Hello, another exciting day of Stat 135, Lecture 7. So let's review what we did last time with sufficiency. A statistic is a function of your data only, and T is sufficient when your data conditioned on your statistic doesn't depend on theta. And we saw that in practice, to show sufficiency, that you try and factor your likelihood function into a part that just involves your statistic and theta, and a part that just involves your data. And so here's an example where we take n points from a normal distribution. We can write the likelihood function in this way, and you can see that we can factorize it so that the sample mean and sample variance are sufficient statistics here. So G and H are as shown here. And why is this useful? It's useful because if T is sufficient, then the Emily estimate is a function of T. In other words, to find the Emily estimate, you optimize the likelihood function, but to optimize the likelihood function, you only need to optimize your function G, because the H part doesn't depend on theta at all. So you only need to optimize the G part, and the G part is a function of T. So this corollary follows from the factorization theorem directly. And what we're going to do today is discuss in more depth about sufficient statistics, and introduce in particular about minimal sufficient statistics, and as well we'll do an introduction to hypothesis testing. So to discuss sufficiency some more, and this is not covered in your book, by the way, we need to understand a little bit about partitions. So I just drew a picture here of, say, a set C. Say that this is representing your outcome space, and I've partitioned it into two disjoint sets, A and B. So the disjoint union of A and B is C. And so you can make this partition finer by, for example, subdividing A into A1 and A2. So I've drawn that below. Conversely, AB is coarser than A1, A2B. So once you start with say a maximally coarse partition, you can make it finer just by adding lines. Just don't erase any lines. Okay, and so what we're going to do below is we're going to start with a maximally coarse partition of our outcome space, which is called the likelihood partition, and any finer partitions that we get from this maximally coarse one is called a sufficient partition, and arises from a sufficient statistic. Okay, so that's the idea. Let's just look at some examples. So I define an equivalence relation between outcomes here. The two outcomes are equivalent if the likelihood functions are multiples of one another. So, for example, let's say that x1 and x2 are Bernoulli theta. So here are the four possible outcomes for x1, x2, and here are their likelihood. Here are their likelihoods, right? Likelihood functions of theta, and notice that 1, 0, and 0, 1 have the same likelihood function. So then they are equivalent, and so I've drawn a line such that I've made my outcome space into 3 equivalence classes, or a partition of 3. Okay? So this is the coarsest partition that we're going to look at, and all subsequent partitions that are sufficient are going to be finer partitions of this one. Okay, so for example, now a statistic partitions your outcome space. For example, if your statistic is x1 plus x2, then we get this partitioning here. So this is a one-dimensional statistic, because x1 squared plus x2 squared is a number. Here's a two-dimensional statistic, x1, x2, right? So that's just the same as your data. That's a two-dimensional statistic. So t of 0, 0 is just 0, 0. And so this really is your finest possible partitioning, right? It's just your data itself. Take, for example, t is x1. So now this is a partition, right? 0, 0 and 0, 1 are equivalent here. But as what we see from the following definition, this last example is not a sufficient statistic, right? Because according to this definition of sufficiency, 0, 1, 0, 0, these are equivalent under T, but not equivalent under the likelihood partition. So the likelihood partition is given here, and we can see that 0, 1 and 0, 0 are in separate equivalence classes. So the only way that we could make 0, 1 and 0, 0 equivalent would be to erase this partition, this line here, but I'm not allowed to erase from my coarser partition. Okay, so so here's some examples of sufficient and not sufficient statistics. You can just look this over. Now, right, so the likelihood partition here is my model for the coarsest partition that I can have. But notice that x1 squared plus x2 squared, or x1 plus x2 for that matter, or x1 cubed plus x2 cubed, those all give an equivalent partition as the likelihood partition. So these are special partitions called minimal sufficient partitions. Okay, so statistic is minimal sufficient statistic if the equivalence class given by T is the same as the equivalence class given by the likelihood. So again, the MSS partition is as coarse as possible. So how to find a minimal sufficient statistic? So here's a recipe. So you take the ratio. So take 2 samples from the same, from your same distribution, your random variable, whatever it is you're looking at. So y1 to yn is one sample, x1 to xn is another sample. Look at the ratio of those 2 likelihoods. So T is minimal sufficient. Okay, T is minimal sufficient exactly when this ratio doesn't depend on theta. So you find this ratio, you just stare at it. Okay, so here's an example. So x1 and x2 are Bernoulli. So I wrote down here what the ratio is, and I'm just staring at it. I'm like, so how can I get rid of theta here? Well, the only way I can get rid of theta is if the exponent for theta is 0. And for that to happen, I need the sum of the yi's to be equal to the sum of the xi's, okay? So I want the sum of the yi's to be the same as the sum of the xi's. So I want to define then t to be the sum of my data, the sum of my sample, right? So that is then a minimal sufficient statistic according to this. Okay, so here's another example. I have a Poisson random sample, and I ask you to find the likelihood, show that t is sufficient using the factorization theorem. Is this particular t a sufficient statistic? Is it minimal sufficient? And find a minimal sufficient statistic. So I think this is all fairly clear here. So I'll just